Okay, so I will say just a few words about Orion X. If you go to orionx.net, we saw, SpaceX, Google X, Orion X, that's where it came from. We try to connect the dots, usually for sort of a senior management type of a person who kind of wants to know the salient points without getting into too much of the details, but kind of needs to be informed by the details. So we look at AI and HPC. As I was just telling Taher, my view is that AI is an HPC application. HPC stands for high performance computing, supercomputing, numerically intensive computing. We'll define it in a bit. But fundamentally, our view is that AI is an HPC application, and quantum computing at the moment is really an HPC library call. And that there's an integration opportunity here that's going to drive the business. We also cover 5G, blockchain, and cryptocurrencies, IoT, quantum. As of recently, we started looking at space technology and such. So the idea is really to connect these dots. That's kind of our background. And that leads to a bunch of work in technology analysis, in market execution, as well as occasionally some commentary on policy, especially as these things become more of a geopolitical consideration as they have become. So let's go back, more back. Suddenly it just went 2 or 3. All right. So that's the title of the talk, Integrated is this the future of HPC? So the high performance computing community, HPC community, is technically deep. It pursues grand challenge problems. It is eager to experiment with promising new tools with an early adopter mentality. This makes it the ideal destination for emerging technologies of any sort in general, and quantum computing in particular. And I'll give you a quick update on what the HPC community is doing with quantum, but you may already know a bunch of that. So this talk is a condensed deep dive into a framework that we have for how HPC works and what it needs and what is the current state of quantum computing in HPC, et cetera, et cetera. Okay, so with that, the focus on this talk is on quantum computing, not quantum sensing, not quantum communication, but quantum computing. And by quantum computing, we mean a programmable device, not a device that does things that we could categorize as computation, but it's sort of built to do just that one thing, because that also will happen, right? Now, over time, that's going to blur, and quantum communication and quantum sensing and quantum may kind of deal together. But right now, our focus, and for this talk, is that. So what is HPC, high performance computing? Our definition is that HPC is the application of mathematical modeling to natural phenomena and business processes. And increasingly, it is impacting all manner of human life. The HPC community is the early adopter community, right? It has led the adoption of many things historically. Open systems, it was the first industry to jump on Unix, even before it was Linux. It was the first to jump on Linux. Cray Research was one of the 2 companies that owned its own Unix implementation. It had bought it from like AT&T years ago. Sun Microsystems was the other one. They led high-end networking, InfiniBand, high-end parallel processing, MPI, 64-bit computing, hierarchical storage management, 3D visualization, et cetera, et cetera. So it has a very good track record of adopting new technologies, working out all the kinks, and then pretty much presenting it to the IT market to go and implement. Storage, there's probably not a single storage product in the market today that doesn't have Los Alamos National Labs footprints on it somewhere, like regardless of what it is. It's like that pervasive in those things. So when you go to a supercomputing show, and the Supercomputing 23 conference, SC23, was just a couple of weeks ago before Thanksgiving, what do you see at this show? Everything. You see everything. You see data center infrastructure, CPUs, GPUs, XPUs, whatever, architecture, systems, storage. And indeed, there was a quantum village at SC23 that some of the vendors were present and was really quite wonderful. This also leads to what I call a fatal innovator's dilemma called, and we actually have a party that we attend the Sunday before SC23 called the Dead Architecture Society. because this community, because it's an early adopter, it has no loyalty. A new product that comes in, they're going to adopt it. Wherever they can squeeze more performance for price, they'll be there. And it's also a community where if you're a vendor, they know more about your products than you do. So that kind of motivates real conversations. They're less prone to hype, less prone to sort of marketing activity. So as a result, HPC can become a really good bridge over the so-called chasm. If you look at the adoption for the IT industry as a whole, and you've got the early adopters, and there's a so-called chasm that you're supposed to jump on, and many vendors have difficulty jumping over it, well, HPC, the curve is fundamentally to the left. So the chasm for HPC is way before the chasm for the actual IT industry. So if you manage to do well in HPC, and they're all early adopters, they're going to want it, they take care of, it's sort of the proverbial, a bicycle enthusiast who buys the bike, asks the shop to disassemble it so they can take it home and reassemble it themselves, because that's what's more fun, right? That's the kind of community. So the early majority of HPC ends up being sort of the chasm of the industry. And as a result, you kind of can look at this kind of a curve, where if you target HPC and then go to the main industry, you have an easier time in sort of being successful. And of course, what is happening is this right now. Because of AI, because of the advances because the interest in HPC applications is a lot more than it was before, and it's permeating more and more parts of industry and society, the whole curve is becoming more of a chi-squared curve rather than a normal distribution, and there is a propensity to be the early adopter even by traditionally conservative companies. The going fast in the digital classical domain, and this is what the HPC community does. They go fast. They do whatever it takes to go fast. So how do you go fast, right? So far, over the past 30, 40 years, the way they've gone fast is that if you look at concurrency on one axis and intensity on another axis, concurrency is just how much parallelism I have. And intensity is how many bytes do I move and how much communication do I do on those bytes. And the more I do, the more the trip makes sense. It's like if you go take a flight to Australia, you probably don't want to just have a 1-hour meeting and come back. You probably want to stay a few weeks to make it worthwhile. That's the kind of a thing. Now, some applications are very well behaved from that standpoint. You want to do a 2D convolution? Awesome. Almost any technology can do that. When you look at all those like 7,000-fold increases in performance in the past, let's say, whatever it was the number, like 7-10 years, that's for a particularly well-behaved application. It's for the kind of application that has very high compute intensity. So if you go from that, compute to memory and then, serial to parallel, the way people have done speed is to go from single node into some kind of parallelism. You do it through traditional models. You can go algorithmic and come up with a new algorithm that is actually faster. Or you can use AI to help you optimize things. But as a result, you end up kind of replicating systems, replicating cores, replicating memory pipes, mixed precision, quantum-inspired streaming data, streamlined instructions, and all manner of architectures pan out. So this is the beginning of the seed for the word heterogeneous. So the heterogeneity that shows up, what we might call modality, but what the HPC community calls sort of heterogeneity, is the different approaches to get speed. And in that context, quantum computing becomes yet another approach to get speed. And that's how the HPC community thinks about this. It's like, I've got one more tool that's going to make some things go fast. And if I take my application and I just like histogram it across, there are parts that are amenable to nothing. They are really just serial, right? Now, the beauty of it is that the part that isn't serial grows faster than the part that doesn't. So if you're familiar with Amdahl's law, it said the part that isn't optimizable is going to take over. If 10% of your application isn't optimizable at all, even if you make the rest 0, you can't hope to do better than 10x performance. So the only way you're going to get 1,000x performance is to reduce the part that is not amenable to optimization to a really tiny fraction. Well, nature is on your side because the part that is optimizable grows way, way faster, right? So if you increase n, the part that, you saw as Scott mentioned, or one of the speakers, it was like 1.73 to the power of n. It was like, whoa, right? That kind of a thing. Okay, so there's a counter argument, there's a counter law called the Gustafson law. And that's by John Gustafson, who was at NASA and other places. And Gustafson's law essentially says that the part of the application that is amenable to optimization grows faster. So if you grow the size of the data set, you will eventually be embarrassingly parallel. And of course, what we are observing, embarrassingly parallel, is for subroutines applications that are so parallelizable, so optimizable, that to not do so would be embarrassing. That's kind of where that is. And basically what we are doing right now is embarrassingly quantum applications right now. And those are the advantages that we do. Okay, so this is working. It's working very well. That's where the GPUs come in. That's where all the the quantum-inspired applications come. But it comes at a very high cost. And this is my other point, is that the HPC community is increasingly moving from I want performance to I want low power. So power, cooling, total cost of ownership are now becoming really big issues. When you go talk to the exascale facilities and the national labs and you say, what does your supercomputer of 5 years from now, 10 years from now look like? They're having a difficulty with power. Right now, you're looking at 20 to 30 megawatts of power. When it runs a benchmark, you can dim the lights of the whole city. So that is a problem. That must be addressed, and quantum computing is a great way to address it, and that reduces the pressure to actually have quantum advantage. Even if you're at the same speed, but you're like 10,000 times less power, suddenly you're very attractive, right? And I think that's one of the reasons why people are pursuing it. So if you kind of look at the upper left-hand side of this chart, this chart says digital on one side, analog on the other, classical physics on one side, quantum physics on the other. And because we are an analyst firm, we need a 2x2. That's a requirement. So the 2x2 is like, okay, the top left-hand side is the digital classical, which is where we've been living for the past 50, 60 years, and it's extraordinarily powerful. It continues to really repel other possibilities. Digital, the combination of digital and analog is mixed signal. This is like what companies like Mythic are doing, where you have some component that is analog that is like integrated with physical. And then the below part is basically all new. That's like, and now if you impose a gate model, you give it a digital flavor. And if you don't, you give it an annealing flavor. But the bottom part of this chart is what we're trying to enable, and it is a net new way of actually making it happen. So what about the applications in HPC? By the way, how am I doing on time? Sorry? 5 more minutes. Okay, so now we have to shift gears. So I mentioned scalar, vector, matrix, tensor. So that actually represents some of the application qualities that you see. So CPUs, coprocessors, GPUs are now doing really a good job with matrix and tensor. And quantum is starting to show up at the higher levels of that. That's kind of the activity. So the grand challenges apps are the stuff that the HPC guys do. The nice thing about those is that they're easily fundable. They're matters of national security and global, they impact humanity in some ways. And then the expected quantum advantage apps that we talk about within the quantum computing circles is computational science, because, well, it's quantum science, sorry. Or optimization, because, well, it's all optimization and it's all probabilities. And then we talk about QML and cybersecurity, which I call the unquantum market, because it actually doesn't use quantum computing. It's just afraid of it. And at the moment, anyway. Except the random numbers. Random numbers are quantum, and potentially you might have algorithms that quantum computers can use for encryption, but not right now. So my advice would be to focus on quantum science and optimization only, because that's where you're going to get traction immediately in the HPC market. And then we go to the basis for the integrated heterogeneous supercomputing. So AI, what is the trends in HPC? The idea with HPC and AI is to enable it, because HPC is an AI is an HPC app. Then use AI. So they're already using mixed precision because AI kind of enabled it and led it, and now HPC guys are using it for their own use. You can use AI to code for accelerators. So sooner or later, we're going to just use AI to code quantum computers for us, so we don't have to, basically. That's already happening for classical computers. Use it to optimize applications, and use it to manage these complex systems, because these systems are themselves quite complex. Then integration. You want to integrate new technologies, accelerators, edge devices that are outside of the data center, and instruments. So scientific instruments themselves are becoming mini supercomputers. The data processing and data reduction that needs to happen when the data is at data inception is really very important. And then integrate other campuses. So if you're looking at Department of Energy and you've got, almost 24 national labs around the country, can I integrate them such that I can use whatever specialization they have in a different lab? And then, of course, sustainability, power, efficiency, cooling, et cetera. So then this is like the HPC quantum examples. Fujitsu has a wonderful hybrid quantum platform. They have 64-qubit system, a 40-qubit simulator, a digital annealer chip, actually, that you can use. Eviden, which used to be called Atos, but they got spun out of Atos in France. They have an excellent quantum computing environment as well, with Captiva, as they call it. And then, of course, NVIDIA has the Q quantum library. And that really is the competition, right? And NVIDIA is the competition. US DOE labs, the ones with substantial quantum computing, Oak Ridge, Argonne, Lawrence Berkeley, but also Fermilab, also Brookhaven National Lab. These guys have significant quantum technology. US cloud providers with increasing emphasis on HPC. That's Amazon, of course, Microsoft, Google, and of course, IBM. European HPC centers, probably the most notable one is Jülich in Germany. And then the Japanese HPC centers, the Riken Center in Japan, and of course China. Not everybody knows everything that goes on there, but we all know that there's a lot that is going on. And did I just get cut off, or did I do that myself? I got cut off. Well, thank you for your attention, for being here. I'll be around if there are any questions, and I'm delighted to be here. Thank you, Q2B.